Okay, so I believe last time you asked me to start explaining this one again with all of the tensions. Okay, so of course we're going to be solving this system. So the first part of it is draw a free body diagram, and the free body diagram has to represent the weight and all of the external forces that are acting on that, because external forces will transfer into the internal forces. So let's look at what's external. So the first one, you have this tension C. You have that right here because it's external, because it's whatever the ceiling or whatever that's hanging from is supplying the force to tension C that's holding it weight, so it's external to the system. So for example, like this tension here in the middle, that's internal because the system is the two pulleys and the mass. Okay, so then you have tension B. Again, here, there is the ceiling is external to the system, holding up the second pulley, so that's going to be one of the external forces. Of course, you're going to have the gravitational force on the mass, and then you have the tension C here. So you imagine like someone's holding the cable, holding it all still. That's external to the system. So when you're looking at a free body diagram of tensions, you're looking at the external forces to the system. Yes, TA is internal. Because that's between one of the pulleys and the mass. So everything that's external is going to translate into that. Right. Now, those three different tension Cs, why are those three different lengths of cable all at tension C? Why are they the same? Same cable. It doesn't matter how many pulleys you wind it through, it's the same cable. Okay. So let's see, what are we trying to solve for? Yeah, it looks like we're trying to solve for each individual tension. So what? We start here. So the easiest one to solve for is tension A. Now, of course, you remember tension A. Look at it. So you see that tension A is one of these ones that you say, well, it goes up and it goes down. Why does it go in both directions? Yeah, so it has to do with your frame of reference. So tension A attached to the weight is pulling up. Tension A attached to the pulley is pulling down, but it's the same tension. So it just really depends on where you're looking at it from. Are you looking at it from the mass, or are you looking at it from the pulley? But just because it can go in both directions, it's still the same magnitude. Okay, so it's pretty easy to solve for tension A, because if you look at the mass, all the mass has on it is tension A and the force of gravity. Okay, so you do your sum of forces in the y direction, and you're going to end up with the magnitude of tension A equals the magnitude of the gravitational force, and that's 1804 newtons. The next part of this is going to show you why pulleys are as important as they are. And honestly, you can look up stories from the Middle Ages and whatnot. These are people who had a working knowledge of science are the ones who were called wizards. And so they would do things like, I can lift that heavy mass. Well, they just put a bunch of pulleys together. And most people in the Middle Ages are going, oh, witchcraft. And it was, you know. So let's start looking at our pulleys one by one, okay? Okay. Actually, I'm gonna move that down. Okay, so I have the pulley on the left, all right? Let's think about the forces on it. Okay, so let's compare that. We're looking at this pulley on the left here, the bottom left. You see how you have tension C up, tension A down? So that is the second free body diagram that we're looking at. And so if I said, well, what if I wanted to figure out tension C?
Those tension C's be the same?
Yes, because it's the same cable snaked through all the pulleys. We're gonna do our sum of forces in Y. Tension C. Tension C plus tension A, and the system is in equilibrium, so all the sum of forces is 0. Now I look at the ways that they're pointed. Remember earlier we set positive Y in that direction. So that's going to give us a positive tension C plus a positive tension C minus tension A equals 0. When I move this around, I'm going to get 2 times tension C equals tension A. Tension C is going to equal 1/2 tension A. And so then I know what tension A is. So tension C is going to be about 902 newtons. And so again, this was part of what used to amaze people in the Middle Ages about pulley systems. Because you have this mass no one could lift. Well, as you notice here, I have 2 pulleys, and that cuts in half the amount of force that I have to use on the side to lift that weight. What happens if I start adding more pulleys? Well, it's like 3 pulleys, you're going to end up with about 1/3 tension A, 4 pulleys, 1/4, so on and so forth. So the more pulleys you add to the system, the lighter the mass is going to become. So now we have tension A and tension C. Okay, what about tension B? So let's go back up and remember tension B is right here. So now I want to solve for that. Okay. So let's draw our second pulley. Okay, and take account of the forces involved here. In between the 2 pulleys, on the left side. So for pulley number 2, this is our free body diagram. So we can say so we're going to have tension C, tension C, E equals 0. And then let's take account of their positive or negative. So you see the 2 tension C's are negative this time. So we're going to end up with minus tension C plus B equals 0. And when I work this through, I'm going to end up with, so let's see, minus 2 C plus B, 0 tension B, going to equal 2 times the tension C, 2 times our 902. And that gets us back to our 1804 newtons. Now, that's how you solve for each of the tensions. Then the last part of this said, show that this is an equilibrium system by showing that all of these forces on the free body diagram, your external forces, sum to 0. So we need our free body diagram. No.
Just a little bit. So tension B is the same as tension A.
Well, we need to remember, what we're going back to now is we're going back to our original free body diagram. So we're trying to show that the forces on this mass equal, sum to zero. What? You do, but you have to start with the theorem, remember?
Yeah, with the theorem first.
Right, and
Plug
then-
it all in.
Yeah, so let's do that. So let's go ahead and draw all our forces on. C. Gravitational force. Okay, so let's think of the sum of our forces. Okay, so it's going to give us C. E gravity. C equals 0. I guess we wouldn't really have to put the equal 0 on there. You just get used to it after you're in an equilibrium system for so long. But the question is, do these four together actually sum to 0? Okay, well, we know that up is positive. So that's going to be tension C, tension B minus gravity minus tension C.
Wait, is tension A this? Never mind.
No, because remember tension.
Never mind.
Okay.
It's a C. I just can't read your.
Oh,
Thanks. That's helpful. Thank you.
I forget I can look at this one.
no, because it's internal. Remember between a pulley and the so you think of everything in the system that can move as internal, and the pulleys will move, the mass will move up and down. So that's all internal. You're looking, so anything external. So like when you're holding the cable, you're providing an external force. When the ceiling holds cables, it's providing an external force. Everything to the inside the pulley system is internal. So tension A is between a pulley and the mass, so it's internal.
We don't account for that.
No. So the first thing we can do is we can say, well, TC minus TC is 0, so those go away. Tension B minus gravity. And tension B was what? 1804 newtons minus gravity. 1804 newtons equals 0.
Wait, how did you know the force of gravity was 1804?
That was something we started with. So we go back up here.
This is what we did on Friday. Was that first?
So 0 newtons.
Yep. So I mean, it shows you that this is an equilibrium system.
Oh.
So I kind of heard what you were saying, Dom, but why is it force of A?
Okay. So again, tension A is going to be internal. Think of your external forces as anything outside the system, such as like if you're holding the cable, you're outside the pulley system. The pulleys and the mass, those are all internal to the system. The gravitational field pulling down on the mass, that's external to the pulley mass system. The ceiling holding up cables, that's external to the pulley mass system.
What's the end of tension C?
The what?
Like, you know how tension C is like does this and it comes down again?
Yeah, so you know that tension C in the middle between the two pulleys, that's internal.
Yeah.
The tension C on one side, let's see, to you, it's like tension C.
One's pulling the wall.
Right.
one's down.
And so the tension C on the ceiling is an external force.
Yeah.
The tension C on the outside, holding, someone's holding that.
Oh, okay.
That's an external force.
Gotcha.
Never had high Chinese food.
And so again, when you're drawing the free body diagram on the mass,
I'm not gonna lie.
you're looking at the external forces translating into the internal, to the system.
I bought it with our sauce.
Okay,
New chapter?
Yep. Acceleration and Newton's second law of motion. Okay, so we've done 1 and 3. We've done laws 1 and 3. Now we're going to look at the more famous one, law 2. All right. So the first thing we need to start with is the idea of a position vector. Okay. So what I'm going to do, it's not great, but I'm going to say you're traveling along that path, okay? So at any point, I can say, well, let's say I'm at that point right there. So any point on the path that you're traveling, you're going to pick an origin, and it can be modeled with a position vector r. So you remember how when I was talking about gravity, I said in the generalized r hat direction? This is what we're talking about. So since we're able to define a position vector, because then of course you're going to be able to take that apart, you're going to be able to do the components, all that good stuff.
Is that an R?
Yes, R. Position vectors are going to be represented with an R. Now you can imagine we could have a position vector to almost every point along this path. Okay. Okay, now what we're going to do is we're going to say, what about a point there? And one there. So what I'm going to have, I have our initial. So you're going to say my initial point was right there, so I can have a position vector going to the initial point of measurement. My final point of measurement, our final, and then what I can define here is displacement.
What is that letter at the bottom?
Yeah. So then I can draw a vector going from the initial point to the final point, and what I get
I hate graphs.
is delta R.
That's what I see.
Now, let's talk about what we mean by displacement versus distance.
You're not.
So your displacement is always going to be a vector subtraction. Your delta R is always going to be a vector subtraction. Your R final minus your R initial. So if you remember how you add vectors, remember you add the X components and add the Y components. Subtraction is the same way. It's just you subtract the X components, you subtract the Y components. And you get your new vector, your delta R. So if you want to think about that, let's say we have components for an initial R vector, initial position vector. Let's then do the same thing for the final position vector. My delta R, R final minus R initial. So what I'm going to get is R final X minus R initial X, I hat,
Too fast, too fast, too.
plus R final Y minus our initial y, j hat. So it's the same format as adding the vectors. You're just going to subtract them this time. So if this delta r is what we know as displacement. So like, let's say you're walking around town. I went this many blocks east. I went this many blocks north. Your displacement is going to be this delta r. You're going to subtract the final vector from the first vector, and you're going to get your displacement. Why is that different from the distance you traveled?
Distance is like moving away.
Right, it's the magnitude of each vector added together. So your distance, you'd follow along the path that you're traveling and measure the entire distance. Displacement is different. So their distance and displacement, different. So take, for example, let's say you started in this room and spent the next 8 hours walking around town, but then you ended up right back in this room where you started. What would your displacement be? 0. So that's why I say, you'll find out we have this thing in physics called work, and it's a fun joke you can play. I mean, if you have a boss who's good natured or you don't mind getting fired, when your boss says you didn't do any work today, if you look down and you ended your work day in the exact same spot you began in, technically you can go, you're right. Work is going to be a vector addition. If you end where you started, it's 0.
So when you're doing that delta R, like your path was fairly straight, but if you did like a curve,
Right.
would you still go straight across to
Yeah,
the dots,
so-
or would you follow your path?
No, what you're gonna do is you're gonna have a beginning point and an end point. It doesn't matter where they are. So let me draw this and let me get rid of some stuff here so you can see it.
So many.
Half is gone.
You have an amino acid in-
So let's say, for example, I did that and that. What you get is still the same, it's still the same operation, and your delta R displacement goes like that. So yeah, delta R does not have to follow the path. Okay, so there we talk about distance versus displacement. So again, your distance would be, your distance depends on the path you travel. Your displacement does not. Your displacement, here's something from chemistry. Displacement you can think of as a state function, which means what? State function. Only depends on what? Your beginning and ending states. Does not matter on the path you took to get there. Distance does depend on the path you took. That's why you could walk for 8 hours and end up with a displacement of 0. So now for a lot of the problems you solve, this can get a lot easier. So let's say X initial, because you, of course, your delta R can break down into displacements in each dimension. So you can have X and Y components of your displacement as well. And if you're dealing in one dimension, you're only finding delta X or delta Y. So let's say we have an X initial there. And then we have one, our final there, our displacement. And so in this case, we would say our displacement is going to be delta X, X final minus X initial, and that would be what? 18 minus 3, 15 centimeters. The other way, so that's a magnitude. What would it look like in vector format? Well, because we're going to the right, that'd be a positive 15 centimeters I had. What if I went back the other way from go back the other way? And then, of course, you could say, you notice that both of them have a magnitude of 15 centimeters. It doesn't matter which way they point. Because remember, your magnitude is going to be just the size of the vector. It does not take into account which way it's pointing. So it's going to be an absolute value. Okay. Net displacement is going to be the sum of all of your displacement vectors. So let's say we go, let's do one there. Let's do one there. We'll do one there. That's your R1, R2. So you have 3 position vectors. Okay, so what are all the displacements that can take place here?
1, 2.
Yeah. That's going to be your delta R 1, 2. No, I have the roots in here. Okay. Let me draw these in first so I can figure out what kind of room I have. So there's my 1 to 2. There's my 1 to 3. There's my 2 to 3.
Did I go back? What a perfect little 3D shape is.
Delta R1, 2. Delta R1 to 3. Delta R2 to 3. So my net displacement in this case my delta R13 is going to equal delta R23 plus delta R12. Okay. And so what is delta R1 to 3? That's R3 minus R1. What is delta R2 to 3? R3 minus R2 plus your 1 to 2, 2 and 1.
You're just saying,
So you look at your delta R, 1, 3 is your total displacement, your net displacement.
What's that number in the 3 minus 2?
Oh, 3 minus 2.
Oh, thank you. I put 3 minus 3 because I was really.
So we can have 3 minus 2 plus 2 is 1. The 2's cancel. So you end up with R3 minus R1, which shows that yes, it doesn't matter how many different displacements you have, your net displacement is going to be the vector addition of all of them. So it gets you right back up to here. So you say, well, now I can have displacements all over the place, and my total displacement after all that's done is going to be the vector sum of all of them. Let's look at the, let's just say we have displacement 1, displacement 2. You're going to add those 3 vectors together. And this adds the way you've been adding vectors. So you're going to add together all the x's, you're going to add together all the y's, you get your total displacement vector. Again, remember the means I pick are pretty, they kind of go with the slide we're on.
so the R1.
So you're saying I look like
plus
that?
R3 is the same as R3 minus R1?
Different example. The R3 minus R1 was to show you that yes, this theorem does hold that your net displacement vector is going to be the sum of all of your individual displacement vectors. So now I'm just saying, let's say you have displacement vectors 1, 2, and 3. Your total displacement will now be the vector addition of 1, 2, and 3. Because of course, you know, each one of those is going to have an x and y component. So just like all of the vector addition you've been doing up to this point, you add together the x's, you add together the y's, you have your new vector. How are we feeling?
No.
I need an example. I can see it.
I think once you start working problems, it becomes more clear. Okay. So let's say we have a vector B. It has a magnitude of 7.1, direction 14 degrees below the x-axis. Which direction will that be in? Which quadrant? 4. Draw that in. Going to kind of eyeball 14 degrees.
Okay, Cal.
Okay. Now we're going to have a displacement. So a vector C has x component negative 1.8 and y component negative 6.7. What quadrant? Negative. 3. So it has a larger y component than x component, so it's going to go more down like this. Okay. So let's see, what are the x and y components of B? Well, that's simple enough. Theta is going to be 14 degrees. Okay, so what do we want to do? What about Bx? What do we want to do?
Cosine, right?
Yes,
Sorry, BX, cosine.
okay, so B is 7.1. Cosine of 14 degrees. You get a Bx of 6.89. If Bx is cosine, By has to be sine. And that's going to give us 1.72, but it's in the fourth quadrant. So what do we have to do to that? Okay, so we have our vector B. It's going to be 6.89 I hat minus 1.72 J hat. Okay, so we have B. Okay, the magnitude and direction of C. How do I do magnitude?
I don't know.
It's like the
Use
thing.
Pythagorean theorem.
Don't give up just yet. You what?
Pythagorean theorem.
Yeah, so we're just gonna CX squared, CY squared.
Okay, good, that's what I said, yeah.
I know, I was just like, I don't know.
Your magnitude formula it stays the same.
Theorem?
That's where it comes from.
Okay, why can't you just say that?
But once you know the formula for magnitude, you can just use it.
That's the.
It's your x squared plus your y squared, square root of the whole thing.
Yeah.
Yeah, I have so many different.
What's the word for it?
Okay, so from the problem, we had a negative 1.8
He puts it in.
squared plus
I'm not gonna do that.
negative 6.7 squared. Square root. The magnitude is going to come out to be 6.94.
See the low light. I see the first play of the year.
Okay, and what about the direction of C? We've already used theta, so we're going to use phi this time. Phi equals what?
Inverse tangent.
What over what?
And you
Opposite over
somewhere
adjacent.
tangent.
Y over x. Negative 6.7 over 8.
It's something.
That's going to give us a direction
Something in my calculator that I'm not.
75 degrees. But then we have to ask ourselves, where is that 75 degrees at? That's just dealing with the third quadrant. Right, because you notice your y component is larger in magnitude than your x component. So in this 75 degrees, 45 degrees is halfway through the quadrant. So this larger angle has to work so it makes the x value larger. It has to be right here. So then we remind ourselves of C vector. Is that? Because the next thing we're going to do, the x and y components of C minus B. So let's draw C minus B in. Okay. How do we do the X and Y components of C minus B?
Just put them.
Boxes and put in those equations that you have to invest in.
Yeah, we're gonna subtract the two vectors. So what are we gonna have? We're gonna have CX minus BX. I had direction, so whatever that is, that'll be our X component. Plus CY, BY, J hat, that'll be our Y component. Okay, so what is our CX? A negative 1.8. What is our BX? That is 6.89. Hat plus our CY minus BY. Our CY is a negative 6.7. And our BY is a negative 1.72, but the negative of a negative plus 1.72 J hat. When we add this up, negative 8.69 I hat minus 4.98 J hat. And so we can say that the X component would be a negative 8.69. Y component will be a negative 4.98. So if we're really building on skills one level at a time. So we started with vector addition. Now we're at vector subtraction. What was that?
When does that vector sit
You watch, vector is going to be your next word on Wordle.
It actually has to be 5 letters.
Even I know that, Clint.
I don't play Wordle.
I got Wordle on TV.
Want a cookie?
I do want a cookie.
No, this one for 7.
So what did part D ask of us?
Magnitude and direction.
Magnitude and direction of the C minus B vector. Okay.
Magnitude.
Oh my gosh. So.
So magnitude of C minus B,
Just plug it in those numbers.
your X's and your Y's.
Yep.
C minus B, X squared plus. Again, it's your X squared plus your Y squared. Take the square root of the whole thing. That's going to be negative 8.69 squared plus 4.98 squared square root. The magnitude is going to be 10.0. And then its direction, well, we've used theta and phi. We use gamma too much, so use beta.
Yes.
We could use zeta.
Hey. It's too late. You are no. Like, let's do A, B, C, D, E. I don't speak.
We have to be careful. Like, for example, you don't really want to use epsilon as an angle because there are universal constants that take the epsilon.
I did it.
So again, it's inverse tangent y over x.
Why don't they use ounces? God damn it. What the fuck? It's like a kilometer. Screw. Let's use cups. One cup of velocity. Six cups.
Theta is going to be 29.8 degrees. Well, let's think about where that's at. So again, your direction is your inverse tangent of y over x. Your magnitude and your direction equations, those are going to stay the way they are. Now, there's two ways we could figure out where this angle is. Let's go back up to our diagram here. The first thing we can say is so you see our c minus b vector, okay? That is a subtraction between c and b. So we see where it's at. So the first thing we could do is draw in another x and y coordinate system. And then we think like, we think, okay, well, we notice that x is larger than y. So the angle is going to have to go in a place, this small angle is going to have to go in the place where that makes that possible. So beta is going to go in there. We could also redraw again, we just take c minus b and move it up to the origin. Your beta is going to have to be there. That's the angle that will facilitate a larger x than a y. Just keep telling yourself vectors are fun. Vectors are fun. And sadly, it looks like we're going to run out of time, so you don't get to your first derivative.
So sad. Oh, the agony.
Just figuring that out.